Now on to our keynote session presented by Professor Simon McIntosh-Smith from the University of Bristol, where he leads the High Performance Computing Research Group, focusing on the advanced computer architectures and performance portability. He plays a key role in designing and procuring supercomputers at the local, regional, and national level, including the UK's national HPC service, Archer. In 2016, he led the successful bid by the GW4 Alliance, along with the UK's Met Office and Cray, to design and build Azimoth, the world's first production ARM v8-based supercomputer. In 2020, Azimoth is receiving a major upgrade, making it one of the largest ARM-based systems in the world while adding the latest ARM processors, Fujitsu's A64FX, and the latest CPUs and GPUs from AMD, Intel, and NVIDIA. He's also a major contributor to the UK's Exascale initiatives, including Excalibur and Azimoth. Exascale systems represent huge challenges in every dimension, in their architectures, in their software stack, and in the algorithms and scientific applications which run on them. In his talk, Professor McIntosh-Smith will discuss several of the initiatives underway in the UK, which are tackling these challenges, including Excalibur and Azimoth, and how these represent an exciting opportunity for research and development. Professor McIntosh-Smith, you may begin.
Great. Thank you very much. Thanks, Brian. Hello, everyone. Nice to be here. So I've got a lot of things I want to try and talk about in the next 25 minutes or so. Really focusing on the exascale space for the UK and what kind of opportunities there are, particularly in the UK. I know there's lots going on in the US and in Europe and in Asia, but we're going to focus on the UK for this talk. So exascale is kind of done, isn't it? I mean, everyone's talked about it. There's lots of systems been announced. Is there anything to do? Can we just go home, take the afternoon off? Well, of course, there's still an awful lot to do, in fact. So while lots of systems have been announced, and I've listed some of the ones here that are destined for Asia and for the US, there's an awful lot of work that comes out of these that we all still need to do. Of course, one of the things to notice about the exascale machines that have been discussed so far is they're very diverse. They're much more diverse than we've had in the recent past, in the last 10 years or so. And the diversity is not just in the architectures, so where we have CPU-only machines or CPU plus GPU machines, but also in the vendors. So we have AMD becoming competitive again and also providing GPUs. We have Intel starting to provide GPUs. And in this set of machines that have been announced, we have almost every combination that you can imagine so far being represented. So there's a lot more heterogeneity and diversity at exascale. And that's just with the machines that have been announced so far. I mean, with the next generations, who knows what other kinds of combinations we're going to see. So for cutting-edge science, the kind of science that we want to do on these machines, kind of the whole point of doing these machines, there's still an awful lot of work for us to do. So exactly what hardware do we need to target? And that's not just selecting what CPUs you might want or what GPUs you might want, but also within those devices, do they have accelerators within them? So do you now have tensor units or matrix units within those processors? And then I think the challenge for software is even bigger than the hardware. So what programming language should you be using to target all of those different architectures? What middleware might you need to use? What MPI libraries? What tasking frameworks? What fault tolerance frameworks? And on and on and on. The list is just enormous. And it's not clear there's any one answer to that question. If you want to target all of those different exascale machines, what's the right selection of software that will give you the greatest coverage, the greatest performance portability, the greatest confidence that that software is going to be around for the long term? There's no clear one answer to all of that. So clearly there's lots of challenges, and in the UK there are a number of initiatives that are running right now to try and address these challenges. I'm just going to talk about a couple of those. First one is Excalibur, which Mark already mentioned. A second one is Azimoth, which was briefly mentioned as well. I'll just describe both of those briefly to give you some idea of what we're up to in the UK. And we'll start with Excalibur. You may have heard this mentioned a few times, and it's a almost £46 million program. It's being led by the Met Office and UKRI. has involvement from UKAEA, which is the UK's fusion energy research group. And it's really focused on software and algorithms. So this isn't a hardware program, this is really a software and algorithms program, and it's to get the UK science space ready for Exascale. It's a 5-year initiative, it's already been running for a year or so, has a number of themes in them, which include things like knowledge integration, defining what the high priority use cases are. So what are we actually going to use Exascale for? What kind of new science is going to be possible that we just can't do today? Also things like what the emerging requirements are for algorithms. There's a whole strand looking at cross-cutting research. So that might cover things like domain-specific languages, fault tolerance, performance portability, those sorts of issues which affect everything. And then also a theme looking at proof of concept hardware. So we've got a bit more runway here. We kind of have several years to get ourselves ready for Exascale in the UK. So we want to be a bit more involved in the kinds of technologies that will be coming out in the future, not just what's available today, not just taking whatever is available at the time, but really being more involved in helping kind of co-design solutions for the future in the ways that the US and Japan have been really good at in the past. So now we've got a little bit more time, we can do that to some extent as part of Excalibur 2. So there are a number of pillars that Excalibur is promoting to get us to Exascale. One is really focusing on the separation of concerns. So this is in developing new codes and algorithms, trying to keep the maths and the algorithms separate from the implementation. And we're seeing increasing success of this approach in a number of different domains. And this gives us a bit more future-proofness, a bit more, it's going to aid things like performance portability and so on. So we think separation of concerns is really important. Really focusing on co-design as well. And I'm not just talking about, say, co-design of software with hardware, but really co-design of algorithms and solvers with implementation experts and computer scientists and so on, all working together, really trying to do a much better job there. Also on the data science aspects, looking at things like whole workflows, not just focusing in on one particular application, but actually looking at the whole workflow in a holistic way, trying to understand, from scientists having an idea all the way through to the end results and the paper being published. How do you deal with all of the different applications that come together, all of the different data flows, the gigantic data sets, but some parts of that problem and so on. So trying to understand the full workflow and not just focusing in on one particular code to get the answers we need. And then finally, and I'm really glad this is in the program, but focusing on people. So not just worrying about codes and applications and algorithms, but actually on the people and the skills they have and the careers they have, and really looking after them and making sure we've got that set of experts who really understand what the problems are and in trying to make this all become a reality. So that's what Excalibur is all set up to fund and to make happen. And there's a number of different activities within those 4 different themes. The high priority use cases are running now, so that's establishing what it is we really want to use Exascale for, what we think the science is that we want to use Exascale to achieve, and building some communities and establishing what those really are. Eventually those will turn into sort of software projects and benchmarks and things like that. Also at the bottom, I'm going to highlight the development of novel test beds. This is the part of Excalibur that I'm the most closely involved with, and I'll come back to that in a bit more detail in just a minute. But the high priority use cases, that part of the project's already rolling, and there's quite a few high priority use case projects that are now underway. This is one area where people can get involved, so I wanted to highlight this early on so that you can see what kinds of science areas people are already looking at. And if any of these areas are relevant to you and interesting to you, you can get in touch with me and I can put you in touch with people leading each one of these themes. But we have things like meshing for Exascale. Meshing is always a challenge, but at Exascale, this really blows up and becomes a really big deal. So the project focusing on that. There's a project looking at materials and molecular modeling at Exascale. There's one looking at continuum mechanics, another one looking at system level engineering, Another looking at basically SPH, so parallel particle hydrodynamics. Another one looking at benchmarking for AI. And this is, we're adopting AI type techniques in more and more places within our workflows. So we want to really get a good handle on that. And there's a project looking at that side of things. Another one looking at lattice field theory for Exascale. A project to take the ExaHype H2020 project and take that to Exascale, so that's ExaClaw. One looking at high energy physics. There's a few more, one for turbulent flows, looking at wind energy. And then from the other side of Excalibur, so looking at Met Office type weather and climate, and the fusion side, there's also a weather and climate project, and Neptune, which is looking at neutrals and plasma turbulence and things like that. So a wide range of different projects getting underway. In the early days, their job is really to build the communities, to find all of the people around the UK who might want to be involved in these areas and getting them to Exascale, and then try and figure out what it is we need to do. So if any of those projects really interest you, if you want to get involved, contact me and I'll put you in touch with the right people. So that's the high priority use cases. There's also the Excalibur hardware and enabling software, or H&ES as we call it. And this is really looking at the testbed side of things. So £4.5 million of the budget has been kept for this H&ES program. That's about £1 million a year. The idea is to fund pre-commercial or prototype engagements with vendors, and to really use that to help get the UK software community ready for when those bits of exciting kind of innovative hardware eventually come to products. So these are quite different sorts of projects to things we've run in the UK in the past. They're really pre-commercial. We don't tend to run many projects like that in the UK. They're also very much co-design activities. So vendors together with might be academics or software developers can propose quite radical things, as long as it looks like it's going to be very relevant to Exascale, getting the UK to Exascale, then it's potentially up for grabs. So we're having some quite interesting things suggested as part of this program, which I'll tell you about some of those in a minute. There's also some benchmarking for Exascale activities within this. I mean, how do we objectively evaluate these innovative bits of hardware if they're so new, if they're pre-commercial, might be quite radical, and might not have anything else we can compare them with. So we're really thinking hard about how we can rigorously and objectively evaluate the value of the things coming through this program, and whether we should take them really seriously for Exascale in the UK. So here's some examples of things that have been funded already. At UCL, there's a testbed focusing on interconnects. That's using Mellanox, building effectively reconfigurable sort of software-defined networks. There's another project in Durham, which is also focusing on interconnect, but in a different way. It's actually looking at Gen Z, building a Gen Z test system, as well as using some of the Mellanox Bluefield architecture to see what we can do with that. This project's already using some AMD servers and GPUs, so we've got some AMD hardware in one of these testbeds as well. Then in Cambridge, Paul Collegiate is running a project looking at file systems for Exascale, which is doing some very interesting things. I'm putting a project together looking at accelerators for artificial intelligence and machine learning using GraphCore. That will be the first time we've had some GraphCore hardware in the UK ecosystem. Mark Wilkinson is leading a project looking at coupling ARM CPUs with NVIDIA GPUs and figuring out what all of the implications are for the software ecosystem. So that's another interesting one. Mark Parsons, who's going to be speaking next, I think, he has a project in Edinburgh looking at another range of accelerators and what it takes to really use those effectively. So that's what's been announced so far, but this is a program where there's basically £1 million funding a year. We'd like to use that to fund between 4 and 6 projects, saying that pre-commercial things, prototype things, rather than just products off the peg. And we're really looking for projects that involve both the company being enthusiastically involved and sort of academic partners. So you can get involved with this in a couple of different ways. You can use any of those test beds that are coming, or you can submit a proposal for another test bed. And we actively encourage people to do this. There's a call open right now, which is closing really soon, within days. But there will be more calls, at least one call a year, possibly more often than that, depending on how many proposals we get each time. So this is an opportunity to do something quite exciting and a little bit different, and to do things that we don't often have the chance to do in the UK, and fund sort of prototypes and test beds, which is great fun. Anyway, so that's Excalibur in a nutshell. Big project, all focused really on software and algorithms, and a little bit on future hardware. And then I wanted to take just a couple of minutes to also tell you about another project which is called Azimoth. So Azimoth is all about advanced simulation and modeling. It's a project to help get codes for high fidelity simulation up to exascale, because there's a challenge that Rolls-Royce had, which they came to a group of UK universities and said, we really need help solving this problem, can you help us? So Rolls-Royce brought together Edinburgh with Bristol, Cambridge, Oxford and Warwick, and a couple of smaller companies as well, CFMS and Zenitech, and said, look, here's our ambition. We want to be able to do full virtual design of gas turbines or jet engines, and we want to be able to do this at high enough accuracy, high enough fidelity, high enough confidence that we could essentially certify the design, right, before we ever make it. That's how accurate we want to be able to do this. We could certify it, we could do all the design in simulation, and then press the button and then the engine starts coming out the back of the factory. So this is today's science fiction. This is way beyond anything that's possible right now for this space. For one thing, the physics involved is really challenging, and there's lots of it, lots of different physics. So there's not just the structural mechanics, but there's thermodynamics, there's CFD, there's all the fluid dynamics of that. Even the electromagnetics of the engine spinning, it becomes a gigantic motor, is really complicated. And you need to be able to simulate all of that and couple it all together on a really complicated, and these engines are some of the most complicated machines that man has ever designed. And we think there's something like 1 trillion degrees of freedom in solving this. So it's hugely challenging. Right now, maybe we can simulate a few of the blades on one of the fans, and we need to be able to do the entire engine. So massively challenging. The universities in Oxford and Cambridge, they're working on the solvers. And Edinburgh, Bristol, Warwick, we're working on all the other aspects of designing the codes, designing the benchmarks, looking at future architectures to try and solve this problem. And we're a couple of years in to a 5-year program. We've made a lot of progress, but there's still an awful lot to do. But eventually, we're hoping we'll get there. So this is a real exascale problem. Back of the envelope, we will need an exascale machine to solve this real industrial problem. So we really need these exascale machines to do this. So that's Azimoth, and it's been a really exciting project so far, and hopefully much more to come from it. So a couple of other things going on in the UK. UK's got a really diverse ecosystem of HPC service provision, and Mark Wilkinson mentioned some activities towards building a tier 0 in the UK, so where we'd have something that would be sort of exascale in the UK. In the UK today, we have a number of tier 1s, which are our national services. There's Archer, which is just becoming Archer 2 at the moment. There's all the Met Office systems for weather and climate. And then there's the DIRAC systems as well, so our tier 1s. But something that you don't hear quite so much about is our tier 2s. We have a very diverse, deliberately diverse ecosystem of tier 2s in the UK. And I'm going to tell you a little bit about those. And this is where we come back to this diversity observation that we started with, that there's a lot of different architectures coming. And so in the UK, we use our tier 2s to explore all those different options and to really take them for a test drive and see how well they work, what they work for, what they don't work for. So I actually PI for Isambard, which has just become Isambard 2. This was our foray into ARM-based technologies. Isambard was the first production ARM-based supercomputer. It's just doubled in size. It's now 21,000 cores, and it's being used like any other production system. Just people apply for time on it. They do their science. They don't really care that it's ARM or anything else. It just works. And that was the whole point of it, is to see whether that was possible and to find out if there are any wrinkles. And that's been working fantastically well to Cray system. We now have over 430 registered users, and the system's basically full all the time, just getting on with doing lots of real science, including recently lots of coronavirus-related research, which is really great. Now, of course, we add lots of new technologies to Isambard 2, including a new rack of Fujitsu A64FX processors. This is the CPU that's inside Arku, so it's the number one system on the top 500. We're not quite the same size, so only 72 nodes in this part of Isambard 2, but that's enough to do some interesting experiments and to do some code porting and to do some nicely rigorous experiments, which is what we really want to do with Isambard. So the nice thing about this system is an Apollo 80, so it comes with Cray's software stack. We get Cray's compiler for ARM, as well as the open source tool, so the LVM-based ARM Clang, and of course all the GNU tools. But nicely, Fujitsu's partnering with us, so we have early access to the Fujitsu compiler on here as well. So this will be one of the only systems in the world where you'll eventually have access to all of the different ARM compilers for Fujitsu A64FX. And I'm actually giving you a sneak peek. This picture is of the artwork on the new rack of A64FX in Isambard 2. And we've not actually shown this to anyone yet. So don't distribute that any further. We'll actually do a press release at some point and give you a proper close-up on this bit of artwork. But it's we've got a nice announcement to come for that. So that's Isambard 2. So that's all part of the Tier 2s in the UK. But we've also got loads of other great diverse systems across Tier 2 in the UK, where we have Intel CPUs, we have AMD CPUs, we have IBM CPUs. Obviously, Isambard's got the ARM-based CPUs. Then we've got NVIDIA GPUs, we've got AMD GPUs. We don't have any Intel GPUs yet, but those will come at some point. Some of the GPU systems are very dense, so DGX-based. Some of them are non-dense versions. So there's a bit of everything. There's non-volatile memories. So anything you might want to try, if it's available today, it should be in one of the Tier 2s in the UK. Porting our scientific software and our algorithms across all of those different architectures and different systems is really good for the kind of health and I guess the condition of those codes. The way you get time on those is through something called Access to HPC. Those calls are twice yearly. They're relatively easy to apply for. You can apply for time on any of those systems. Generally, it's sort of millions of core hours on the Tier 2s, more for the Tier 1s. So it's very easy to get access to these machines if you want. Now, just to kind of finish up, I wanted to say something a little bit more kind of forward-looking. I'm going to start with some observations from Hennessy and Patterson and their sort of acceptance lecture when they were given the Turing Award in 2017. And their acceptance speech was titled, "A New Golden Age for Computer Architecture. Domain-specific hardware-software co-design, enhanced security, open instruction sets, and agile chip development." And the link's on this slide, and if you've got 40 minutes, it's worth watching this talk if you haven't, and they say some very interesting things. But their observations are that, well, we're running out of steam a bit on single-thread performance. So we're going to have to get creative about where our advances are coming in the future. And they were suggesting more architectural diversity in terms of accelerators and things like that. And of course, this has been going on for a while. In fact, if you look inside your iPhone or your mobile gadgets, the processors inside there have been very heterogeneous for a long time, for many, many years. A system on chip is essentially a very heterogeneous device where this is an Apple A12 chip. The CPU cores, actually, they don't take up an awful lot of the chip, just this little bit in the middle. The graphics processor is a bit bigger, but most of the rest of the chip is everything else, more highly specialized. So when we look at a server chip, it's nothing like this yet. It's mostly filled with very general purpose processor cores. But there are some interesting recent trends. For example, tensor cores, these are basically accelerators within GPUs. So we've got accelerators in our accelerators now, and they're designed to make tensor operations or vector matrix or matrix-matrix operations go a lot faster than you would do just in a general purpose instruction set. And these seem to work really well. And we expect to see more of this in the future. And in fact, recently, Intel and ARM have already announced their own matrix multiply units. I think the ARM one's called SME, Scalable Matrix Extensions. I can't remember what the Intel one's called, but it's like an extension of AVX. And these are going to be potentially really important for getting more performance in the future. So how do we target that with software? And it's kind of obvious you could do it through a library, but could you compile code to this? That's a bit tougher, that's a bit trickier. Not just the accelerators, but what kinds of data formats they're using, what kind of data types. Can they use reduced precision in some way? If you're double precision today, could you use single precision? Could you use half precision? If you're using different kinds of, if you're targeting different kinds of machine learning, maybe the alternative floating point formats will be best for you at reduced precision, and so on. So there's a lot more that's coming. That's just in the sort of general purpose context. But if you're targeting very specific applications, say artificial intelligence or machine learning, you can become even more specialized. And there's quite a few examples of this recently, from Google's TensorFlow unit to GraphCore to Intel's Nirvana projects. They're all focusing specifically on these areas, trying to make things like TensorFlow or PyTorch go really fast. And then you can become even more extreme. Some details from GraphCore's latest, their second generation technology, just announced in the last month or two. They have 4 of their second gen chips in one pizza box, and that gives them a petaflop of basically 16-bit floating point in just one pizza box. I mean, that's pretty impressive, and that's for about $35,000, I think. So that's actually pretty good going. The second gen IPU, just looking at one of their chips, it's nearly 60 billion transistors. I mean, this is crazy stuff. 900 megabytes of on-chip fast memory with tremendous bandwidth to that, and that 250 teraflops of 16-bit floating point in one chip, or I think about 62.5 teraflops of single precision, and that is IEEE 754 as well. So some amazing things that are coming. But how on earth do we harness all of these diverse solutions for doing our science? At the end of the day, that's what all this is about, right? We want to do some great science, solve some really challenging problems, and make the world a better place. And there are lots and lots of really interesting, really tough challenges in making all of this happen. So anyway, just some key takeaways from all of that. There are lots of exascale-related activities in the UK. I think Mark Parsons is going to tell you more about that in a minute and say a bit more about Tier 0. But you can already get involved in projects like Excalibur. There's things like Azimoth going on, etc. There's all the Tier 1s and the Tier 2s, which you can get involved with. We need to get our users and their codes and their algorithms ready for this future of diverse architectures, diverse vendors, possibly even diverse software. How do we do that? That's a big challenge. And then finally, we've got increased heterogeneity, and that's even inside our CPUs and GPUs. So now we have accelerators within accelerators. What's that? Is that accelerator squared? I'm not sure. So loads of challenges, but lots of good things going on inside the UK that you can get involved with. And with that, there's just some more information. If you want to find out more about Excalibur, there's a sort of prototype website which tells you about things like the hardware and enabling software program, how to submit a bid, how to get in touch with the existing test beds. If you want to know more about what my group does, our website's there. Or you can email me, I'll put you in touch with anyone I've mentioned today. And if you follow me on Twitter, I just generally use that for high performance computing related things. And that's everything I had. So thank you very much. I need to dip in and out this afternoon because I'm doing some interviewing for somebody to support Isambard too. So I need to go and do an interview occasion, then I'll be back. I'll be here some of the time. Thank you.